Viewer. It's a video on thermodynamics lecture series. If you are interested in the topic enthalpy, sit relaxed, make yourself comfortable, watch, enjoy, and learn. Over to the topic now.
So what is this enthalpy? Mathematically, enthalpy is equal to sum of internal energy plus product of pressure and volume. It is a property of the system, of course, extensive property. Therefore, we can define specific enthalpy of the substance denoted by symbol H is equal to U plus PV. A unit of specific enthalpy is kilojoules per kilogram. For an ideal gas, we know PV equal to RT. V is the specific volume. Therefore, in specific enthalpy equation, instead of PV, we can substitute RT, which gives H is equal to U plus RT. And if you observe this equation, earlier we discussed U, internal energy, is a property of the system and it's a function of temperature only. Apart from this internal energy, what is present in this equation are temperature and gas constant R. So it is also a constant. Therefore, enthalpy is also a function of temperature only. Because by definition H is equal to U plus RT, U is a function of temperature and here also temperature is present. So enthalpy is a function of temperature only. Now, total enthalpy, capital H, is equal to product of mass and specific enthalpy, which is equal to U plus PV. So M is the mass. Unit of total enthalpy H is equal to joules or kilojoules, can be expressed in kilojoules also. Now we are going to define a term called specific heat at constant pressure. So what is the definition? It is the rate of change of specific enthalpy H with respect to temperature when the pressure is held constant. Mathematically, we can write like this. C suffix P is the symbol for specific heat at constant pressure, which is equal to dou H by dou T with respect to pressure. That means at constant pressure. So Cp or C suffix P is the specific heat at constant pressure is an extensive property of the system. So this definition of specific heat at constant pressure can be rewritten in differential form like this. So dH at constant pressure is equal to integral Cp dt, and the limits of integrations are T1, T2. The product mCp is equal to Cp is the heat capacity. So mCp is the heat capacity, which is denoted by the symbol capital C suffix P. And the unit is Joule Kelvin. So heat capacity of the system at constant pressure is denoted by C suffix P. So having defined enthalpy and specific heat at constant pressure, we will now look at what is called heat transfer during constant pressure process involving only PDV work. In order to derive a formula for heat transfer during constant pressure process involving only PDV work, consider a piston cylinder arrangement. So some fluid, maybe a gas, maybe an ideal gas, is present inside the piston cylinder arrangement. Suppose if you add heat to this system, remember we are interested in heat transfer during constant pressure process. When you add heat, energy crosses the system boundary, and remember, energy can neither be created nor be destroyed. Therefore, this energy is stored in the system, and because of this heat addition, the volume increases. I'll once again tell you this volume increases, but if you carefully noticed, the size of the piston has increased now. So when it was at the initial state, the size of the piston is less. After expansion, the size of the piston is more. Why? Because when you add heat, it increases the pressure, but it is a constant pressure process. Remember, pressure equal to load by area, therefore load equal to pressure multiplied by area. In this example, area of the piston is constant. So when the pressure increases, load increases. Or in other words, in order to maintain the pressure constant, the piston size or the weight of the piston increases. Now, for this expansion process, we can apply first law, which can be written as Q, that is, the heat transfer is equal to U plus W. In differential form, dq equal to du plus dw. But we know the work we are considering in our example is only PDV. Therefore, this PDV can be substituted instead of dW. And also we know specific enthalpy H is equal to U plus PV. And this can be written as dH is equal to du plus dPV. And this can be differentiated in UV form, which gives you dH is equal to du plus PdV plus VdP. Since it is a constant pressure process, or before that, instead of this du plus PdV, we can substitute this dq. Therefore, this dH can be rewritten as dq plus VdP. And of course, it is a constant pressure process. Therefore, this is 0. And hence we can write dH is equal to dq during a constant pressure process. Or in other words, dq at constant pressure process is equal to dH under constant pressure process is equal to integral Cp dt, and the limits of integrations are T1 and T2. Or in other words, what we can say is heat transfer during constant pressure process increases enthalpy of the system. Heat transfer during constant pressure process increases enthalpy of the system. Remember, in this constant pressure process, we are considering only PDV work. Now we are going to define another specific heat called specific heat at constant volume, which is defined as the rate of change of specific internal energy with respect to temperature when the volume is held constant, and it can be written mathematically as C suffix V equal to dou U by dou T at constant volume. So C suffix V is an extensive property of the system, and from this what we can write is du in constant volume process is equal to integral Cv dt, and the limits of integrations are T1 and T2. So change in internal energy during a constant volume process is equal to integral Cv dt. The product mCv is equal to capital C suffix V is the heat capacity of the system at constant volume. Now we are going to study about the heat transfer during constant volume process. Consider again a piston cylinder arrangement and a system, maybe an ideal gas is confined within this piston cylinder arrangement shown in red color, and the process we are looking at is constant volume process. Therefore, there will not be any movement of the piston, or in other words, since it is a constant volume process, there is no rise in weight. And for this constant volume process, we can apply first law of thermodynamics. That can be written as Q equal to U plus W, in differential form dq equal to du plus dw, and this dw is equal to 0 because volume is constant. Again, we are considering only pdv work, and dv, change in volume during a constant volume process, is 0, and hence dw is equal to 0. From this, we can write dq equal to du. Therefore, we can say dq at constant volume process is equal to change in internal energy in constant volume, which is equal to integral Cv dt. So the difference in heat transfer during constant volume process is equal to change in internal energy. That is what written here. Heat transfer during constant volume process increases the internal energy of the system. That means when you add heat, it increases the internal energy of the system. So what we discussed is enthalpy, specific heat at a constant pressure, specific heat at constant volume, heat transfer during constant pressure and constant volume processes, assuming only PdV work is happening during these processes. From the ongoing discussion, we can say enthalpy is related to heat. And this enthalpy is equal to internal energy plus PV. That is the definition. When heat is added to the system at constant volume process, heat transferred is equal to change in internal energy, U, and hence increases. By definition, H is equal to U plus PV. And heat transferred during a constant pressure process is equal to change in enthalpy. Next, we will study about perpetual motion machine of first kind. So what it says, there can be no machine which would continuously supply work without some other form of energy disappearing simultaneously. What is the meaning of this one? It says energy is conserved. Consider a piston cylinder arrangement, and if you confine a gas inside this piston cylinder arrangement and heat is added, the piston can be raised by adding heat. Raising of weight is nothing but work, and that work is realized due to the addition of heat. So heat energy is converted into work. So one form of energy is disappearing and another form is appearing. The converse can be no machine which would continuously consume work without some other form of energy appearing simultaneously. Finally, we will discuss about what is energy of an isolated system. So an isolated system is separated from its surroundings. And for an isolated system, first law can be applied, and the mathematical form of that first law is Q is equal to del E plus W. Since it is an isolated system, there is no interaction either in the form of mass or in the form of energy, and hence Q and W are 0, and hence delta E equal to 0. That means E is constant. Energy of an isolated system is constant.
Now, the takeaways from the lecture on the topic enthalpy. Enthalpy is a measure of heat content of the system. Denoted by the symbol H, enthalpy is equal to a sum of internal energy and the product of pressure and volume. Enthalpy is an extensive property of the system. If a system undergoes a constant pressure process, then the heat transfer during the process is equal to change in enthalpy. And if a system undergoes a constant volume process, then heat transfer is equal to change in internal energy of the system. Therefore, heat transfer in a system is always accompanied by change in enthalpy. Also, we discussed perpetual motion machine of kind 1 is impossible. And finally, we discussed energy of an isolated system is constant. Thank you.